Hi, welcome to today's lab on measurement and spreadsheets. So you may already know a little bit about spreadsheets, and if so, that's great. If not, don't worry too much about it. But you may already understand that spreadsheets are really good for accounting. If you're a business person and you're doing accounting, spreadsheets were originally developed for just such calculations, right? Keeping track of your money. Turns out that spreadsheets are a super powerful tool that can be used for far more than accounting, and they're really great for doing physics labs and doing certain kind of calculations with science. So in this physics lab, what we're going to be doing is talking about measurement and spreadsheets, and we're going to be using the spreadsheet to, well, we're going to be actually given some data that we assume you took from measuring length, like the distance a ball travels. So that's a length, and then there's going to be time in that. The distance a ball travels, that's going to take some time. So we give a measurement for time. And then also we could talk about measuring like cylinders, spheres, blocks. We can measure a block, measure three sides of it, length, width, and height of the block, and calculate a higher order quantity from that, volume, right? And so you could measure length and time, calculate a higher order quantity from that, velocity or speed. Yeah, and so spreadsheets is going to give you a powerful tool for that and for manipulating data of almost any kind. Here in the physics lab, you collect data. If you collect it and take it down on a spreadsheet, then you can plot that data to visualize it. You can make calculations based on that data, like you could calculate velocities from length and time measurements. You could calculate volume from measurements of length, and then you could calculate densities from measurements of length, making a volume, and then with the weight of an object, it's mass. Density is mass divided by volume. So let's get into that. Here's the handout for today's lab. This shows the parts, so we got exercises 1 through 3, and this exercise 1's got 2 parts, and you can see the points associated with those right there for you. And if you're doing this lab online, then what you're going to do is make a spreadsheet that's going to be pretty much looking like the example one I'm going to make for you, and then you're going to submit that as a file, and that will count as your lab report. So here you can read through this, and that's going to tell you a little bit about spreadsheets. And here's the first data we're going to start working with right here once we get into it. But let's start even back a little before that. Let's go back to basics and think about, okay, what are the kind of things we can measure? Well, here obviously we're measuring length. Okay, and then we can think about, well, how do we do that? How do we go about measuring length? I don't think you'll be too surprised to find out that you'll measure length with something like this most of the time. In fact, there's actually only very few things you can truly measure in science, period. There's, in fact, SI, Standard International, or System International, I guess if you like, if you want to be French about it, defines 7 units that comprise all of science. So 7 things you measure that make everything else. And it seems like there's so much stuff you can measure because you can, but those things all kind of crack down to these base dimensions, and they get built up from that. So one of the most fundamental base dimensions, as you can imagine, is something you'd measure with this right here. So here's this thing, here's this ruler, and we could measure this piece of sticky tab with it. Let's see if we can agree on what that is. All right. I don't know if you can see, but I'm measuring that. Well, it looks like it's measuring out at about 5 centimeters to me. Not sure how good that's showing up for you there. I'm seeing 5 centimeters. And this thing measures to the nearest 0.1 centimeter. So I measured that as 5 centimeters. How would I write that down? You just write 5 centimeters. Let's call it X. So let's call what I measured X. We'll call what I measured X. And here it was 5 centimeters. And there really seems to be no problem with that. I just measured it with that ruler and came out with 5 centimeters. But whether I state it or not, there's actually some uncertainty associated with this measurement. Whether I say what it is or not, it has to be here. And you might be able to see why in a second. Okay, so there's plus or minus some uncertainty associated with that. And why does that have to be there? It seems almost obvious, right? But here's maybe a way I could make it truly much more obvious. What if I said it was 5.017 centimeters? Okay, I measured with that thing. The thing's a ruler. 5.017 centimeters. What's the problem with that? You look at that and go, well, that's a lot of precision, isn't it? For just that ruler you saw, I was just like holding it up in front of a camera, and everything looked a little bit sloppy. And you're saying you're measuring to the thousandths place centimeter precision? Seriously? No, it's impossible, really, especially in this situation, because there's an uncertainty associated with that measurement. So this is not a real thing. Well, what's this uncertainty? Well, that's really up for the experimenter to state what it is. You have to figure it out for yourself. If no one says what it is, there's this thing called a rule of thumb, and say that the uncertainty on my measurement is 1/2 the least tick, or 1/2 the smallest tick. I'll just call it tick. And in the case of that ruler, it's hard to resolve in this camera, but if you were actually here with me, you could count those, and you would see that there's 10 tick marks in between each 1 centimeter spacing. So each tick mark is 1/10 of a centimeter. Right, this measures to the nearest 0.1 centimeter. And so for this particular case right here, the uncertainty of our measurement, here x, whatever it is 5 centimeters, is 1/2 the least tick. If I don't have any other way to get it, I'm just going to use the rule of thumb right here. This is rule of thumb for getting the uncertainty. Just a quick and dirty rule that you just throw in if there's nothing else around. It's 0.05 centimeters. So whether I stated it or not, there was an uncertainty associated with my measurement. And since I got 5 centimeters, that would have been 5 plus or minus 0.05 centimeters, if I use the rule of thumb. Now, honest to say, in this particular case that we just unfurled for ourselves right there, the way I made that measurement, I really feel like it was a lot more sloppy than that. I don't feel like I got to this close of precision. So I'm perfectly justified in stating what I really think the uncertainty was. I think it was probably something more like, something big. Like I'll give myself the benefit of the doubt and call it 5 plus or minus 0.1 centimeters. And really, if I'm going to write it like that, in that case, I could go ahead and show how many sig figs would be legit associated with that calculation. 0.1 centimeters. 5.0 plus or minus 0.1 centimeters. And now you can see why we have 2 sig figs here pretty clearly. Yeah, because this 0.1 is kicking on the door of the first decimal place of precision here of our measurement. So that's always there. So anytime you're doing a lab or anytime you're making a measurement of any kind, this uncertainty is always associated with the measurement. So anytime you're measuring something, what you're really measuring is your best guess on the measurement plus or minus some uncertainty on that measurement. And oftentimes you won't state what this uncertainty is. You'll just write down what your best guess is, right? So there was probably would have been no complaint if I just said x equals 5 centimeters, right? I just measured that thing. But really, legit in the lab, this is what was really going on. And if I want to be, if I'm doing laboratory work, I'll want to go ahead and state it like that. Let's go ahead and begin working our laboratory exercises together. Here's the first exercise in the handout. So what we're going to do is I'm going to work through these exercises with you. You can pretty much just follow me along, follow along with what I do in Excel. And then if you're doing this lab online, you can go ahead and just include a file of your spreadsheet for the work we did in this lab. There'll be, in the last exercise, the data you use will be a little bit different than the data I use. But other than that, everything will be pretty much just the same. And I only do that last one that way, just so I can make sure and you can make sure that you understand what we're doing and you have a legit handle on how to use Excel for this lab. So here's the first exercise. What we did here evidently is made a bunch of measurements of length. So I opened a spreadsheet here. This is an Excel spreadsheet. If you don't have Excel and you don't want to go ahead and pay for that, it would be perfectly fine if you use some other kind of spreadsheet. Like for example, Office Libre has a perfectly good suite of Office tools that are comparable to Microsoft Office. So if you didn't want to get Microsoft Office, you could get Office Libre. Just type Office Libre in your browser. Make sure you don't get anything, any funny business when you download stuff. But if you have any questions, you could just ask me about that or give me an email if that's something you wanted to do. Anyhow, most of us could go ahead and have Excel. Microsoft Office is the industry standard, so it's if you can get it like we got here, go ahead and use Excel. Probably most of us can. Okay, so what we did here is we measured, these are all of our lengths. Those are these values for X we had over here. So I want to go ahead, so I entered all these values, and you can go ahead and enter these values into your spreadsheet like I got them here. There's 8 values. And if we needed to count on the values, we could do, I could put a label right there I call data point, and then go, okay, this is data point 1, and I want to just count, 1, 2, 3, 4, and so on. So here to do that, I could just type, I could just start going in 2, enter 3, enter, and so on. There's really no need to do that though in Excel. Really the way you want to do something like that in Excel is using the power of Excel, and that's using the power of formulas. So anytime you want a formula inside a cell, what you do is just start off with an equal sign. That lets Excel or your spreadsheet know that whatever's coming next is going to be a formula. This formula is pretty simple. I just want to take this number, I just click on, here I'm clicking on A2, that's the cell that has 1 in it, and then to that I add 1. Okay, and that's, okay, so it's this plus that is 1. 1 plus 1 is 2. Now look what happens when we fill down. Right, every one of these cells, it goes, okay, for this cell I go to the cell above me, that's got a 3, and add 1 to that. Right, so you can see the pattern. That's a pattern. It does this pattern and fills it down, and then that just gives us our data point count. Now over here I want to put in length, so I'll just type that in. So this is our length, and that's in units of centimeters. Measure our length in units of centimeters. Oh, well, look at that. So now I typed in, so here's a label. That's good. It tells you what's coming down that column. So data labels are good. But here, notice I cut this label off. I learned this trick from Mr. P. Well, there's a couple things you could do. You could just actually click on that and drag it over, right, and drag it however you like it. But there's an easier way to do it, just to auto format it, is you just double click that. Once you see that crosshair, you double click it, and it automatically resizes the cell for you. And notice I'll just do that to this one because you can see that the length that this so length is fitting in, but our centimeters units that we have to add is not fitting in. So now we have length in centimeters. And would it be fine if over here just to include length like this, so with no units? No, we need to have the fact that this is centimeters. Otherwise, that column doesn't mean anything. Maybe you'll understand what it means today, but tomorrow or a week from now or whenever, time will pass, you'll come back and look at this, it'll say length, and you won't have any idea what units these are. It could be inches, could be centimeters, could be meters, whatever. You don't know what they are. No one else, and no one would know what they are. So it's very important to include units. Why don't we need units on that one? Well, sometimes you have things that aren't units, like counting numbers. This is just a counting number. It's just a label labeling these data points. So clearly we don't need it for that. Okay. Let's consider our data points and try to figure out what we're trying to do with them here. So it says that what we did was we let a ball free fall for the short time interval, 0.11 seconds, and we measured how far the ball traveled during the time that it dropped. We did it 8 times, and then we collected all these data points, 3.69, 3.68, down to 3.67 centimeters. And now we're going to, how should we report our best estimate for how far the ball will typically travel during this time? And here the time is, again, 0.11 seconds. Well, are you seeing it? It comes to me right away. You might pick one in the middle. So they go from 3.66 all the way up to 3.69. I mean, we could pick one in the middle, like 3.67 or 3.68. But the typical way you do it is to take the average value of all these. How do you get the average value? Well, straightforwardly, you just add all these numbers up and then divide by the number of points. So here it'd be just add all these up and divide by 8, because there are 8 of them. And you might be tempted to do that in your calculator. For sure you'd be tempted to do it in your calculator if you didn't know how to use Excel. But here we're learning how to use Excel. If you already know how to use Excel, then you're going to feel great. Yeah, we're going to go straight to Excel for this. So let's figure out how we're going to do this in Excel. Actually, I've already did it here. Let me just get rid of all this, and we'll just start over again. So here's where we are. We got our 8 data points, and we want to find the average value of this data. So our average length, let's call it L average. I'll label it right there and put the value right here. Here I want to calculate the average value of all these data points. So the way you do it is with Excel, you put an equal sign in the cell where you want the value. That lets Excel know you want to do a formula right there. Then you can start typing the formula. If you're guessing, okay, it must be something like average. Yeah, it is. And here you can see, as soon as I start typing, Excel offers me different choices. And I can see there's the one I want, average. That's the one. It says, okay, the average of number, blah, blah. So I want the average of all these numbers. So the way I could get it is click on the first one and then shift click down to the last one. Or you could drag. There's different ways you can do it. You can play around with it. That's the way I do it. I start with the first cell, and then I go down to the last cell, hold down the shift key, and click on the last cell that I want to include. And here I could close parentheses and hit enter, and it'll give me the average value there. But let's go back a second. I'll just redo it just real quick if you're watching this. So I'll go here, shift click down to here. Oh, and here, and then up here you can see it's the average. And if I click enter right now, Excel will automatically put in the parentheses there for me, because it's so simple. It knows how to autocomplete that. Won't even ask. It already knows that's what I want. Okay, so there's the average value, 3.68 centimeters. And now let's think about how we could record this in our lab notebook, including the uncertainty. Here we have the average value. That's our best guess on how far the ball drops in that much time. But there's some uncertainty. There's uncertainty associated with that. So let's work on figuring that out. Alright, so our average value, which we used Excel to calculate, was 3.68 centimeters. Now, what about the delta? So remember, anytime I write down a result, whether I state it or not, there's an implied uncertainty associated with that result. Sometimes I'm going to want to go ahead and write explicitly what the uncertainty is of my measured value. So here, this is the average of 8 trials far the ball went in centimeters. So right now, if I don't have anything else besides this number right here, what I could do is I could use the rule of thumb to say, okay, the uncertainty of this measured value would be 1/2 the least tick. In this case, okay, and so this X is. So what would the least tick be in this case? Actually, the least tick in this case is implied by the precision of this number. This number is measured to the 100th decimal place of centimeters. So that means the least tick of whatever my measuring device was is implied to be 0.01 centimeters. And if I divide that by 2, at 0.01 centimeters, then that means that my uncertainty, just using the rule of thumb, is 0.005, and the units would be centimeters. That's okay to write it like that. But the implication of writing it like that, in this case, would be that my measurement is my best guess. In this case, my best guess is the average, plus or minus my uncertainty, centimeters. So that's how I would get the uncertainty using the rule of thumb. But there's other ways I could get the uncertainty. So let's say, I don't know, let's say I don't believe that rule of thumb for this particular calculation. Another way I could get the uncertainty might be something like this. I could go, okay, my uncertainty is my biggest x, I'll call it x max, minus my smallest x, x min. So that's the spread on the data, if you will, the spread on the length measurements, and then divide that by 2, because I'm going to do plus or minus of it. That would be a good estimate for the uncertainty. So what would that be? Looking back at our spreadsheet, we could see that the biggest value is 3.69, and looks to me like the smallest value is 3.66. So in that case, what I could do is go, okay, then my delta x, that comes out to be 0.015 centimeters. But as a matter of fact, technically, you shouldn't have any more than one significant figure in the uncertainty. That's a general rule. So if I'm being technically correct, I need to round that to the nearest one sig fig, which would be 0.02. So then if I was using this rule, I would report my x equal to 0.02 centimeters. And you can see that's quite a bit less precise than the rule of thumb. And maybe this is better. Maybe this is the way we want to go. We know that our measurements weren't that precise, and we don't trust the rule of thumb. We feel more confident about this. So going back to our lab handout, you see what we did. We went ahead, and this is just showing, it's basically the same thing, just showing you the steps. Here's a write-up where I just went through and physically did it. And you can follow along in your own spreadsheet and do what we just did here. So that's going to calculate the average value like we did. And then we could report the uncertainty in this way. I just looked at the rule of thumb one, but let's say you want to try to get the uncertainty this way. And how would we do that in Excel? Okay, I just did that by hand. Let's go back and see how we could do that in Excel. So what we want to do is calculate the uncertainty based on the biggest number minus the smallest number divided by 2, just like I did it by hand over on that virtual piece of paper. But here I want to do it in a spreadsheet. So here I'm going to have a spreadsheet handle the calculation for me. So the way we're going to do that is I'm going to put my uncertainty in this cell. I'm going to call it delta L for uncertainty. And then I'm going to let Excel know I want to do a calculation by putting in an equal sign. And I'm going to need an open paren for this, and I think you'll see why in a second. Okay, so what I want now is the biggest value in this list. So Excel can find that for me. I can see what it is. It's 3.69. But say this was a list of 500 numbers or something like that. Then you don't want to have to look for it by hand like that or by eye. What you could do then is just get a function here. Start typing in. I know I want it to be the maximum one, and I see it's got this function max. So the maximum of what? The maximum of all these. Okay, and I'll close paren around that. And so that's the biggest one, and now I want to minus the smallest one. So I'll start going, okay, mi, I think it's minimum, so that's the function. Max minus min, and then of what? All these, the same ones. Okay, and I need to close paren. So what I want, because what I want to do is I want to take that big number minus that small number. Once all that's done, then I want to divide by 2. If I didn't put the parentheses around it, what it would do then is just go, if there was no parentheses around this max and min, overall parentheses, what it would do is it would just take the max and then it would subtract half of the min from that. But that's not what we want. We want max minus min all divided by 2. Now we'll enter it. And there you can see it's what we calculated with our calculator a second ago. We just used Excel to calculate our average, the average value, and then we used Excel to calculate the uncertainty based on the method of just going take the biggest one minus the smallest one and divide by 2, split the middle, and we came up with the uncertainty of 0.015. Technically, uncertainty should only have one sig fig, And so here we tried the thing where we click on it and try to decrease the decimal place, and look, lo and behold, it doesn't round properly. So I have to look maybe for another way to do it. So I'm going to call, and notice I relabeled it to del big, because that's the biggest way, or I can see off the top of my head, to calculate the uncertainty. That's saying I'm going to be quite generous in how uncertain I think things are. So let's look at how we might do it. So we'll type equals here and look for some way to round things. And we see, okay, there's these functions, round, round down, and round up. I'm just going to try round and see what happens. So round, I want to round this number. Let's say digits. Let's say I round it to 2. Let's see what happens. Okay, it didn't work right. So I'm not sure what's going on. Let me try one of the other ones. Let me try round up. Round up. Oh, round up worked. I'm not really sure why. I don't want to get so far afield, digging into the insides of Excel to understand. But I know that that's what I wanted to happen, right? I wanted this to round up to 0.02. And actually the number of decimal places, it should just stop at the end. So now I'm just going to go ahead and decrease those decimal places with this decrease arrow right here. And that's my uncertainty. Okay, and so we could see how we would report it if we were writing it by hand. We could even, report it here in Excel, figure out how to do the notation details, but I'm not going to worry about that. But the answer would be 3.68 plus or minus 0.02 newtons, calculating the uncertainty this way. Again, the rule of thumb was 1/2 the least tick, so if I use that uncertainty, it's quite a bit less. It would have been 0.0005 centimeters. So we got that. Let's go on to the next exercise. We're going to calculate the error one last way using the standard deviation. And we're going to do that because when you have a data set with a quorum, you're within your rights to use the statistical determination of uncertainty. And the way you do that is you use this thing called the standard deviation. You calculate the standard deviation, and then you determine the statistical error from the standard deviation according to these formulas you see right here. So here's a standard deviation, here's a statistical error. Here, n is the number of data points, x sub I is any one of the points of your data set, x is the mean value of the data set, and this is how you calculate it. And if you stare at that guy for a little bit, you'll see it's like a geometric mean. It's kind of like a Pythagorean theorem, c squared equals a squared plus b squared, except that it's for more dimensions. In this case, it's going to be 8 dimensions because we have data points. What it essentially is it gives you the average distance of any one of your data points from the mean. If you look at this, here's the square. By doing the difference and then taking the square, that gets rid of any negativity of some of the ones, because if you weren't to square them, then some would be above the mean, some would be below the mean, and then in the the limit of infinite data points, basically this thing would come out to be 0 because you'd have as many minuses as pluses, and those would knock each other out. That's not what you want. You want the average distance that a data point lies from the mean value, and you can kind of see that's what this is. This is the number of data points. This -1 here, that has to do, it's called Bessel's correction, and it has to do with the fact that you don't actually have all the possible data points you could have collected. Like we could have collected 1,000 data points, and we only collected 8. So the real mean might be a little bit different. So here, by dividing by this slightly smaller number, this would be the number of data points -1, that gives us a little bigger estimate for the standard deviation. That is how far a typical data point lies from the mean. Okay, and then to get to the standard error, we just go ahead and divide that by the number of data points. And if you thought about for a little while, that does, with these two things together, that does represent then really the average distance that a data point will lie from the mean. Anyhow, let's just go ahead and try the example let's try it for our example. So you can see here I got these formulas here, and we'll just go ahead and work out what this would be for our particular example. Okay, so I'm just gonna look back on our data here, and Just go ahead and start writing this out. Here I'm just doing this for all the data points. Right here I'm just going to put dot dot dot. It means I got to do this 8 times 1, 2, 3, 4, 5, 6, 7 plus the last one. You can see the pattern. I'm actually going to be doing this on my calculator, so I'm not going to actually write out every term here, but here's the last term that would go in. And you could look back at the data set and see that it would look like this. That's the last term in our data set. And so all this together, so I'll put parentheses around all this. All that has to get divided by 7. And then we got to take the square root. It's kind of a monster, but you see this is just following this procedure. Just add all these up. So take the mean minus the particular data point, then square it, and just add, so the mean minus the value of the data point for all the data points. Square them, add them all up, divide by the number of data points minus 1. Here there was 8 data points minus 1 is 7. So that's what that is. I did it on my calculator. 0.011 centimeters. Remember, all these have units of centimeters. Just for brevity, I didn't put the units in there, but maybe I could have put it on the last one. Technically, I could put it in here. Centimeters, just sneak it in there. Okay, so all this comes out to units of centimeters. And so that's my standard deviation of my data. Meanwhile, the standard error, so this sigma, the standard error, that is literally going to be what we take to be the uncertainty on the data, the delta x. So the delta x is equal to this, what they're calling it sigma sub x here, which is equal to the sigma over square root number of data points. So this delta x is just putting in the things, putting in the numbers at 0.011, and then I got to divide that by root 8. 0.011 divided by root 8 comes out to be 0.004 centimeters. Okay, you see we just did that by hand. Would I be asking you to do this by hand in the lab? No, basically never. I just did it by hand this one time, just to show, technically you can do it. There's a formula for it and a procedure. We can do all this in Excel, and it's going to be a lot easier for us in Excel. So let's check out how to do that. So there's one last way then that we're trying to report the error associated with this data set, and that's using the standard error calculated from the standard deviation. So it could be that Excel has a formula for calculating the standard error directly. I'm not exactly sure what it is. I fiddled around with it and never quite felt satisfied that I found it. But I do know the one for standard deviation, and I do know how to calculate the standard error from that. So I'm just going to go ahead and do it directly that way. So what I'm going to do is I'm going to calculate the standard deviation and then the standard error from the standard deviation, and from that, the standard error is our uncertainty, and then once we have that, we can show how to go ahead and report the answer by hand, say if we were writing it down in our lab book, which if we had a real lab book, if you're online you don't have a lab book, but if you had a lab book, this would be how you'd want to report the answer in it once we get to the end. Okay, so to get the standard deviation, remember I just did it by hand the long way. We would never normally want to go through that if we don't have to. So how would we do it here in Excel? Okay, just start typing equals. That lets Excel know we want a formula right there. And so I'll just start looking for it. Let's see if I see it. Standard D. So it's STD. It's one of these. STDVA. I believe it's this one that gives me the one that I want. Okay, so standard deviation and this VA one. Well, I know that that's the regular one that I want to use. So it's the standard deviation of what? All these data points. So what's it going to do? Okay, so I could just actually I could just enter it right there, and that's what it just calculated the same thing we did. Right? 0.011 rounded standard deviation, 0.011 centimeters rounded. Now to get the standard error from that, I just do, okay, it's equal to this thing divided by the square root, and here square root is a function, so square root of the number of data points. In this case, the number of data points is 8, as you can see, so it's going to be square root of 8. Okay, and so that's the standard error. Now here, your error, the plus or minus that you're going to add or subtract on to the end of your mean value to show your uncertainty, should technically only ever be expressed to 1 sig fig. So let's see what happens when I use the decrease decimal button here. Okay, great. For some reason it rounded that one and not this one. Ask the makers of Excel why that happened. But anyhow, so that's it. So now using the standard deviation to get the standard error, we could see how to report our final answer. Now let's go ahead and show how we would do that right now. So you see we used Excel to calculate quite readily what we have right here. Right, so Excel did all this work for us. Here I did it the long way, right? Just go through this procedure. Average value minus the data point for all 8 data points, right? And they're squared. Add them all up. Take the sum of all that stuff, divide it all by the number of data points minus 1, and you take the square root of all that, and then you get the standard deviation. That turned out to be 0.011 rounded. Right? Go back to Excel, and you see that's what we just calculated right there. Okay, so now, but we have everything we need to know, so how do we go ahead and report our final answer? So remember, so say here, if it's x, then whether we write it this way or not, when we write down, so x is equal to something, it's equal to our best guess plus or minus the uncertainty. And a lot of times we would just write down our best guess, right? If I measure, 3.86 centimeters, and I just write that down. Whether I write it down or not, there's just some implied uncertainty. Here we calculated it using statistical methods. We used the standard deviation, and then from that we got the standard error. So in this case, x would be 3.68, that's the mean value, plus or minus the standard error. So that's that. So that's our answer.